Right now, deep at the center of our galaxy, a black hole 4 million times heavier than our sun is quietly tearing a pair of stars apart. One is captured forever. The other is hurled outward at over 4 million miles an hour, fast enough to escape the Milky Way completely, never to return. Astronomers imagined this in 1988. It took 17 long years to find one. Today, only a handful of stars have ever been confirmed to come from this exact place, flung out of the only galaxy any of us have ever called home. One of them is 14 billion years old, nearly as old as the universe itself, and it was just discovered. Tonight, we follow its impossible journey out of everything it has ever known. Unlike those runaway stars racing off alone forever, you don't have to go anywhere tonight if you'd like more evenings like this one. A quiet like and subscribe keeps us finding each other again. Get comfortable now and let your eyes rest. In 3, 2, 1, liftoff. Step outside on a clear night, away from the glow of streetlights, and look up. The stars you see tonight are the same stars your grandparents saw. The same patterns, the same familiar shapes, wheeling slowly overhead the way they have for as long as anyone alive has been alive to watch them. Find the Big Dipper. If the sky where you are still lets you see it, and know that your great-grandparents once found it the exact same way, from a porch or a field or the back of a pickup truck, on a night no different from this one. There is something deeply comforting in that continuity. Whole lives get measured against that sky without anyone ever saying so out loud. People fall in love under it, sit up worrying under it, make promises and quietly break them under it. And through all of it, the sky itself never seems to change, never seems to keep score, never seems to age the way everything underneath it does. The night sky feels like the one part of the world that never changes, a fixed backdrop behind every human life that has ever been lived, from the first campfire on the first cold night to tonight's quiet drive home with the radio low. It feels permanent. It feels, in the truest sense of the word, settled. It is not settled. Right now, somewhere in that familiar sky, a small handful of stars are doing something almost nobody notices, and almost nobody could notice, even knowing exactly where to look. They are leaving, not fading the way. An old star quietly dims toward the end of its life, not dying in the sudden violence of a supernova. They are simply, quietly racing outward, away from the galaxy that made them, at speeds so extreme that nothing in our galaxy's gravity, not even the combined pull of hundreds of billions of stars working together, is enough to call them back. Wherever they are headed, they will get there completely alone, and they will never again share a sky with another galaxy's worth of stars the way we do tonight. Something is throwing them, and the culprit sits exactly where you would least expect a culprit to hide, at the very center of our own galaxy, in the one place that every star in the Milky Way, including our own sun, has been quietly circling for the whole of its existence. Our own sun sits far out from that center, in one of the galaxy's quieter spiral arms, tracing a lazy, unhurried orbit that takes hundreds of millions of years to complete even once. From out here, the center of the galaxy looks like little more than a dense, hazy smudge of light, low in the summer sky, easy to overlook, easy to mistake for nothing more than a bit of extra starlight. We spend so much of our lives looking outward, toward the planets, toward the more distant stars, that it is easy to forget the galaxy has a center at all, let alone that something is happening there right now that reaches all the way out to the stars we can actually see. We call that place Sagittarius A star. Despite the name, it is not a star. It is a black hole, roughly 4 million times heavier than our Sun, and yet packed into a space not much larger than the distance between our Sun and its innermost planet. It sits inside a crowded, glowing region astronomers call the galactic bulge, a dense swarm of stars, gas, and drifting dust packed together far more tightly than anything in our own quiet corner of the galaxy. Out here, near our own Sun, the nearest star to us is trillions of miles away, a lonely, comfortable kind of distance. Near the center of the galaxy, stars crowd together far more closely than that. Close enough that a night sky there, if any planet could survive such a neighborhood, would blaze with thousands of stars bright enough to cast shadows, wrapped in glowing clouds of gas lit from within by young, hot stars, and the deep, restful darkness we take for granted out here would barely exist at all. By the 1980s, astronomers already had good reason to suspect something enormous and completely invisible occupied that exact spot, tucked behind thick curtains of gas and dust toward the constellation Sagittarius, from which it takes its name. They could not see it directly. They could only see its influence on the stars nearby, the way you can tell a heavy stone is resting under a blanket without ever lifting the blanket to look. It is worth remembering just how new and how genuinely unproven the very idea of a black hole still was in those years. Plenty of respected scientists were still not convinced that anything as strange as an object millions of times heavier than our Sun, crushed down into essentially a single point, could really exist anywhere in nature, in any galaxy, let alone quietly, at the center of our own. The term itself had only entered common scientific use in the 1960s, and by the time Hill sat down with his own calculations, physicists had only really convinced themselves that black holes existed at all, because of a single, much smaller example. An X-ray source in the constellation Cygnus, first detected in 1964 and eventually traced to an invisible companion pulling on an ordinary bright star nearby. That object was not even widely accepted as a genuine black hole until the end of 1973, and it was famous enough that two of the era's most respected physicists placed a public wager over whether it really was one, a bet that stood unresolved for the better part of 2 decades. That single, modest, stellar-sized black hole was the entire body of solid evidence physicists had to stand on. A black hole millions of times heavier, quietly sitting at the center of our own galaxy, remained, in 1988, nothing more than an educated guess, however carefully reasoned. What almost nobody was asking, in those years, was a stranger question than whether it was really there. A quieter, stranger question that would take one particular scientist working almost entirely alone to seriously consider. Not whether something massive was hiding at the heart of the galaxy. Everyone serious about the problem already suspected that much, or at least suspected it was worth taking seriously. The stranger question was this: could that hidden giant every so often reach out and simply throw a star away? That question belonged, for a long time, to one man, working with nothing but a pencil, a notepad, and the patient, unforgiving rules of gravity. His name was Jack Hills, a theoretical astrophysicist at Los Alamos National Laboratory in New Mexico, a place better known in the popular imagination for nuclear physics and the history of the atomic age than for predicting the fate of distant stars. The laboratory sits high in the mountains of northern New Mexico, under some of the clearest, darkest air in the country, the kind of sky that has drawn astronomers and physicists to that part of the world for generations, though Hills himself needed nothing more than his own office to do this particular work. Hills belong to a different, quieter tradition within astronomy, the tradition of the theorist, the kind of scientist who makes discoveries without ever pointing a telescope at the sky, because his laboratory was mathematics itself, and his instrument was a sharpened pencil. While observational astronomers spent their nights at mountaintop observatories, waiting on clear skies and steady air, a theorist like Hills could make his discoveries at an ordinary desk in broad daylight, armed with nothing but the equations that already governed how gravity behaves and the patience to follow those equations to conclusions nobody else had thought to chase. Hills was no stranger to the far edges of what gravity can do. Years earlier, he had spent a great deal of time thinking carefully about the outer reaches of our own solar system, the faint, frozen region of icy debris that begins far beyond Pluto and extends into the true darkness between the stars. A portion of that region, the inner shell of it, still carries his name today. Astronomers call it the Hills Cloud, and they still use his calculations when they try to picture the coldest, quietest suburbs of our own sun's family of worlds, a place so far removed from the warmth of daylight that the objects drifting there barely qualify as belonging to a solar system at all. But by the middle of the 1980s, Hills had turned his attention much closer to home, toward the crowded, violent center of our own galaxy, and toward a question that most of his colleagues had simply never thought to ask. Here is the idea Hills carried into 1988, and it is worth sitting with for a moment, because it is stranger and more elegant than it first sounds. Picture two stars bound to each other, circling a shared center of gravity, the way partners circle each other on a dance floor, never quite letting go. Pairs like this are not rare, and you may already be more familiar with one than you realize. Look back at that Big Dipper you found earlier. The second star from the end of its handle, a star called Mizar, is not one star at all, but at least two, orbiting so closely together that for generations, long before telescopes existed, people with especially sharp eyes used it as a simple test of their own eyesight, since spotting its faint companion star with the naked eye took real, careful looking. Roughly half of all the stars visible in tonight's sky are believed to have a companion of their own, in exactly this way, locked into a slow, patient orbit that can last for the star's entire lifetime. Two stars born together, aging together, and, under ordinary circumstances, expected to stay together for as long as either of them exists. Now, imagine one such pair, drifting through the crowded heart of the galaxy the way pairs like this do, wandering closer and closer to the enormous, invisible mass at the center, without either star having the faintest way of knowing what lay ahead of it. Gravity does not treat two partners equally when the distances involved become that extreme. The reason such violence is even possible comes down to something remarkably simple. Gravity grows enormously stronger the closer you get to its source, far faster than most people realize. Move twice as close to any massive object, and its pull does not simply double, it quadruples. Move 10 times closer, and the pull becomes 100 times stronger. Near an ordinary star, this steep rise in strength matters very little, because nothing ever gets close enough for the difference to add up to much. Near a black hole holding the mass of 4 million suns in a space barely wider than a city, that same steep rise becomes ferocious. The partner slightly nearer to the black hole feels its pull far more violently than the partner slightly farther away, and at the distances involved near the center of the galaxy, slightly nearer can mean the entire difference between a star that survives and a star that does not. Hills calculated that this imbalance could become so severe, so suddenly, that the partnership itself would be torn apart in the time it takes to round a single curve, faster than either star could have any warning that anything was wrong. This kind of gravitational violence was not entirely without precedent. Even in 1988, engineers already understood and had already used a far gentler version of the very same trick. Uncrewed space probes leaving our solar system routinely swing close past a planet, borrow a small amount of that planet's own orbital speed through the precise geometry of the encounter, and depart faster than they arrived without the planet losing anything anyone would ever notice. Hills was describing the same basic principle, gravity converting a close approach into a change of speed, but turned up to an almost unimaginable degree, with a black hole standing in for the planet, and an entire star standing in for the spacecraft. One star, Hills proposed, would be caught, pulled into a tight, permanent orbit around the black hole, folded into the dense, whirling swarm of stars that already circles at close range, trapped forever in the very neighborhood it had only ever meant to pass through on its way to somewhere else. The other star would not share that fate, freed of its partner all at once, and carrying away a portion of the tremendous gravitational energy that the doomed pairing had once held between them. That second star would be hurled outward, off into the wider galaxy, at a speed that had no real precedent anywhere else in astronomy. One partner absorbed into the crowd forever, the other cast out of it forever. Gravity, in a single stroke, choosing two completely opposite fates for two stars that had, until that moment, shared exactly the same one. There is something almost unbearably specific about that image. A partnership that might have lasted for billions of years, ended in moments, its two halves sent toward two entirely different futures, one swallowed into permanent company, the other exiled into permanent solitude, neither one ever knowing, from that moment forward, what became of the other. Hills worked through the numbers, and the numbers themselves were almost hard to believe. A star, born and raised deep in the crowded, gravity-soaked heart of the galaxy could, according to his calculations, be sent flying outward at speeds exceeding 1,000 kilometers a second, well over 2 million miles an hour, and in the most extreme cases, he calculated speeds as high as 4,000 kilometers a second, nearly 9 million miles an hour. For comparison, our own sun drifts through the galaxy at roughly 220 kilometers a second, a speed so ordinary among stars that it barely registers as motion at all. Hills was describing something that would leave that ordinary galactic traffic behind entirely, the way a car doing 10 times the speed limit leaves the rest of the highway behind it, vanishing from the rearview mirror of everything around it. There was another wrinkle to the prediction, one that made it even more remarkable. Escaping the black hole's immediate grip was only the beginning of a star's journey. To actually leave the galaxy for good, an ejected star would then have to fight its way against the combined gravity of everything else in the Milky Way, the hundreds of billions of other stars, and the vast unseen reservoir of dark matter that outweighs all of them combined, all of it pulling gently but insistently inward, all the way out to the galaxy's outer edge. Hills accounted for this too. The speeds he predicted were not merely fast enough to escape the black hole's grip. They were fast enough to outrun the gravity of the entire galaxy at once, a much higher bar to clear, and clear it with room to spare. Hills understood, too, that even if his physics were entirely correct, an event like this would still be rare. It required a very particular kind of near miss, not just any star, but a bound pair, not just any encounter, but one that carried the pair close enough to the black hole for its grip to matter, without carrying them so close that both stars, and not just one, were destroyed outright. The zone in which this could actually happen was a comparatively narrow one, a kind of gravitational tightrope only a small fraction of the galaxy's countless binary pairs would ever walk. Most such pairs, across the galaxy's entire history, would simply never wander anywhere near the center at all. Of the ones that did, most would pass by too far to be affected, or plunge in too close and be destroyed together rather than separated. Hills was not describing an assembly line. He was describing a rare, precise accident of orbital mechanics, repeated only occasionally across the vast span of the galaxy's history. He gave these hypothetical wanderers a name of their own, a name astronomers still use today without ever having to explain where it came from: hypervelocity stars. Stars too fast to belong anywhere. Stars fast enough, in theory, to outrun the very galaxy that built them, cross its entire visible disk, and keep going long after every other star nearby had settled back into its familiar, orderly orbit. It would have been a remarkable idea even as pure mathematics, the kind of elegant proof that circulates quietly among specialists and then gathers dust in a journal that almost nobody outside the field ever opens. But Hill saw further than that, and this is really the heart of why his idea mattered as much as it did. He understood that if even a single such star could ever actually be found, out among the hundreds of billions of ordinary stars in the galaxy, and its path traced backward across the sky to the exact point it had come from, it would do something no telescope of his era could do directly. It would prove, almost beyond reasonable argument, that the invisible giant at the center of the galaxy was real, and that it behaved exactly the way the mathematics said it should. And it would do more than simply prove the giant was there. A star's exact speed and the precise direction it had come from could be used to measure the black hole's mass with real precision, the way you might judge exactly how hard someone had thrown a ball, simply by watching how far and how fast it flew. Astronomers would not just be confirming a shadow, they would be weighing it. There was a still larger question hanging over all of it, one that reached beyond any single galaxy. If gravity behaved at the center of the Milky Way exactly the way Einstein's equations said it should, even in conditions this extreme, that would be one more confirmation of a theory that, by the 1980s, had already passed every test thrown at it. If it did not, if a hypervelocity star turned up moving in some way the equations failed to predict, that would be a discovery of an entirely different order, the kind that reshapes physics itself rather than merely confirming it. Not suspected, not inferred indirectly from the wobble of nearby stars or the crackle of radio waves. Proven, in the plainest way astronomy can prove anything, by the unmistakable fingerprint of a single star still carrying, in its own extraordinary velocity, the complete record of exactly what had happened to it tens of thousands of years earlier and tens of thousands of light years away. Tens of thousands of light years is not a distance human experience has any real reference for. It is roughly the distance across our entire galaxy's visible disk, the kind of gulf that light itself, the fastest thing in existence, needs tens of thousands of years to cross. A star flung from the galactic center tonight, at the speeds Hills described, would still be making its way outward long after every person reading these words, and their children, and their children's children, had lived and died many times over. This was never going to be a short story. It was always going to be one that unfolded across a span of time that made a single human lifetime look almost meaningless by comparison. Every other piece of evidence available at the time was the indirect kind, the kind that requires trusting a long chain of careful reasoning rather than pointing to a single, undeniable object. Stars near the galactic center did seem to move a little strangely. On the rare occasions astronomers could measure them at all through the dust. Radio waves did crackle from that exact spot in ways that suggested something unusual and compact. But indirect evidence, however carefully gathered, always leaves room for another explanation, another theory, another decade of careful argument among specialists who are, by nature and by training, reluctant to agree on anything they cannot measure directly. Hills was describing something categorically different, a single star caught in the act, its own extreme velocity serving as a kind of confession, evidence that would need no chain of reasoning at all to interpret. That was the appeal of the idea, and also its enormous difficulty. A theory is only as useful as the evidence that can eventually confirm or break it, and in 1988, no one, including Hills himself, had ever seen anything resembling a hypervelocity star. He had described something that should exist, according to the patient, unforgiving logic of gravity. He simply could not point to a single example of it. Predictions like this one do not always turn out to be true. Astronomy's history is full of careful, elegant ideas that never found a single piece of supporting evidence and quietly faded from the conversation, remembered, if at all, as a clever guess that simply did not pan out. Hills had no guarantee his own idea would not join that long-forgotten list. He could only wait. The patient kind of waiting good theories often require for evidence that might still be years away or might never arrive at all. The years that followed were quiet ones for the idea, at least as far as the outside world was concerned. A prediction sitting patiently in the scientific literature, unconfirmed, occupies a strange kind of limbo. It is not wrong, because nothing has disproven it. It is not right, because nothing has proven it either. It simply waits, the way a sealed letter waits on a shelf, its contents already decided the moment it was written, but not yet known to a single living soul. Finding an actual hypervelocity star, it turned out, was a far harder task than predicting one had ever been. The galaxy holds hundreds of billions of stars, and nearly all of them move in the same broad, orderly current, circling the center the way the hands of a clock circle its face, unhurried, predictable, and entirely unremarkable. A hypervelocity star would be the rare, almost impossible exception to that rule. One point of light, somewhere in that entire enormous crowd, moving in open defiance of everything around it, and carrying no outward sign of that defiance except its speed. Finding it would be something like standing at the exit of a packed stadium long after a game has ended, watching tens of thousands of people flow steadily toward the parking lot in one unbroken current, and somehow trying to spot the single person walking the other way, against the crowd, back toward the empty field. In a galaxy of that size, such a star could be anywhere. It could be faint. It could be impossibly distant. It could simply be lost in the ordinary glare of everything else in the sky, indistinguishable, at a glance, from any of the hundreds of billions of stars going about their unremarkable business all around it. Even spotting a star's position precisely is only half the challenge. Measuring how fast a star is actually moving through space, rather than simply where it happens to sit in the sky at a given moment, requires reading something subtler, the way its light stretches or compresses depending on whether the star is racing toward us or away from us. The same basic principle behind the changing pitch of a train whistle as the train rushes past on the tracks. Extracting that kind of information from a single point of starlight, faint and half buried among the ordinary population of a crowded galaxy, was, in the 1980s, still slow, painstaking work, done one star at a time, at the eyepiece of instruments, built to examine light star by star, rather than by the thousands. Astronomers in the 1980s, and for a good while afterward, had no real way to systematically scan the whole sky for one unusual point of light moving at an unusual speed. Photographing the sky, one patient plate at a time, the way astronomers had done for most of the 20th century, could reveal where a star was. It could not, by itself, reveal how fast that star was moving through space, not with anything close to the precision this particular search would require. The great sky surveys that would eventually make that kind of search possible, the digital catalogues, the instruments built specifically to measure the motion of enormous numbers of stars at once, did not exist yet. The techniques were not refined. All that existed, for now, was the prediction itself, sitting quietly in the scientific record, waiting for the technology and the patience to finally catch up to it. And so, the idea waited, not forgotten, but not yet proven either, filed away in that particular corner of astronomy reserved for predictions too compelling to dismiss and too unconfirmed to teach as settled fact. Somewhere out there, right now, a partnership that once seemed as permanent as any of the stars overhead had already been broken, or was about to be, or would be broken 1,000 years from now, or 1,000,000. The galaxy does not keep a calendar. It simply keeps happening, indifferent to who is watching, indifferent to whether anyone back on a small blue planet in one of its quieter arms has yet worked out how to notice. Somewhere out in the galaxy, if Hills had done his arithmetic correctly, a star exactly like the one he had described might already be sailing through the dark at this very moment, carrying the story of its own escape to absolutely no one. Its light would already be crossing the vast distance toward Earth, years upon years before a single astronomer would know to look for it, let alone recognize, once they finally saw it, exactly what they were looking at. Hills had done everything a theorist can do. He had followed the mathematics as far as it would honestly go, and then he had written down exactly what it told him, without knowing whether he would ever see it confirmed. All that stood between a strange idea on paper and an actual, confirmed star in the sky was time, better instruments, and someone, somewhere, willing to go looking for one small point of light, moving just a little too fast, in a galaxy that had never once made finding such a thing easy. But before following that search any further, it is worth pausing on the moment itself, the one Hills had described only in the language of mathematics. What would it actually look like if his equations were right? Not the abstract idea of a star being flung away, but the actual event, the specific, violent handful of hours in which one ordinary partnership, circling peacefully for who knows how many millions of years, met its end. There is no better way to understand a piece of physics than to watch it happen, slowly, one step at a time, even if the actual event, when it finally came, would have felt to any observer unbearably fast. Picture the pair as they had always been, up until that point. Two stars, born together out of the same collapsing cloud of gas, spending their entire existence circling a shared center of gravity, closer to each other than our own sun is to its nearest neighbor, closer perhaps than our sun is to some of its own planets. From their own point of view, if a star could be said to have one, nothing about their situation was unusual. Millions of pairs across the galaxy live out their whole lives exactly this way, orbiting steadily, changing little, dying only when one or both of them eventually run out of fuel, generations upon generations from now. For as long as either star could be said to have existed, this was simply what life was. Two points of light, bound together, tracing the same unhurried loop through the crowded inner galaxy again and again, indifferent to the passage of centuries, the way only a star can be. Human history, in its entirety, from the first cave paintings to the most recent election back home, would not even register as a rounding error against a single one of their orbits. Pairs born and raised this close to the galactic center also tend to differ from pairs like our own Sun and its distant neighbors. The gas clouds near the center are unusually dense, unusually turbulent, and unusually rich in raw material, conditions that tend to produce stars far more massive and far hotter than an ordinary, modest star like our own Sun. Many of the stars that live out their lives in that crowded neighborhood burn blue-white rather than yellow, live shorter, more furious lives, and shine brightly enough to stand out even across enormous distances, a detail that would later matter a great deal to anyone trying to spot one of Hills's hypothetical wanderers among the ordinary crowd. Neither star had any way of sensing danger, because in the truest sense there was no danger yet, not for a very long time. Stars have no eyes, no instincts, nothing resembling caution. They simply follow the path gravity lays out for them, one moment folding into the next, for as long as the universe allows. The pair's orbit around the galactic center might have taken thousands of years to complete just once, an unhurried, sweeping loop through the crowded inner galaxy, indistinguishable from a great enough distance from the paths of countless other pairs making the same slow circuit. On most such loops, nothing remarkable happens at all. The pair simply swings past the center at a comfortable distance and continues on, unchanged, for another few thousand years, and another, and another. This particular pair's undoing began long before either star came anywhere near the black hole in the slow, almost accidental drift that carries stars through the crowded inner galaxy over immense stretches of time. Pulled by the combined gravity of everything around them, tugged gently off course by other stars passing at a distance, a pair like this could spend ages wandering, gradually working its way inward toward the galaxy's dense, crowded core, without either star ever intending to go anywhere near the thing waiting there. And then, at some point, on some ordinary orbit around the galactic center that looked no different from 1,000 orbits before it, the pair's path curved just a little too close. Astronomers actually have a preview of what a moment like this looks like, though it played out on a far smaller stage in our own solar system, in full view of Earth. In the summer of 1992, a modest, unremarkable comet swept in close to Jupiter, the largest planet in our solar system. The comet's name was Shoemaker-Levy 9, named for the three people who would go on to discover its aftermath the following year: Carolyn Shoemaker, Eugene Shoemaker, and David Levy. Nobody was watching closely enough at the time to see what happened during that 1992 pass, but the evidence of it would become impossible to miss. The comet had wandered near enough to Jupiter that the giant planet's gravity pulled far harder on the near side of the comet than on its far side, the same basic imbalance Hills had described for a binary star nearing a black hole, only here acting on a single, loosely held together ball of ice and rock rather than two separate stars. Astronomers watching that summer, had any been watching closely enough, would have seen nothing dramatic happen at all. Just a small, distant smudge of light passing a little closer to Jupiter than usual, indistinguishable from any other unremarkable close approach. The comet could not hold itself together against that difference. It came apart. A single star, wandering that close to a black hole alone, would very likely meet a far more violent end than a captured comet, torn apart entirely by the very same kind of tidal force. Its material stretched into a long, glowing stream and eventually pulled in and consumed, a genuinely destructive event astronomers have separately observed happening to lone stars elsewhere in the universe, bright enough to be seen as a sudden flare from across enormous distances. A star traveling with a partner has an option, A lone star does not. Instead of being torn apart itself, the pair can be torn apart from each other, the doomed partnership absorbing the violence so that neither individual star has to. It is, in its own strange way, the difference between an object being destroyed and a partnership being ended. And it was precisely this distinction between shredding a single star and separating a pair that Hills had spotted where others had not. When astronomers finally spotted the comet in March of 1993, it was no longer one object. It was a broken chain of more than 20 separate fragments, strung out one after another like beads, a shape so distinctive that observers nicknamed it the string of pearls. Every fragment in that chain had, until recently, been part of a single, whole comet, barely a mile across. Jupiter's gravity alone had done the breaking, quietly and without any explosion, simply by pulling harder on one side of the comet than the other, until the comet's own modest gravity could no longer hold it together. For nearly a full week in July of 1994, those fragments came home to finish what had begun 2 years earlier. One after another, days apart, they struck Jupiter's clouds, each impact releasing more energy than the entire world's stockpile of nuclear weapons combined. Telescopes on every continent turned toward Jupiter that week, joined by the Hubble Space Telescope and by NASA's Galileo spacecraft, already en route to the planet and perfectly placed to watch it happen. The impacts left dark bruises on Jupiter's face, some larger than the whole of Earth, visible through backyard telescopes for months afterward. It remains, to this day, the only time humanity has ever watched two bodies in our own solar system collide, predicted and observed from beginning to end. That comet's undoing offers a small, visible echo of exactly what Hills was describing, scaled up almost beyond imagining. Where Jupiter is large among planets, Sagittarius A star outweighs an ordinary star by roughly 4 million times. Where the comet was a loose, fragile ball of ice, easily overwhelmed by a difference in pull from one side to the other, two stars locked in orbit are held together only by their own mutual gravity, a bond that feels unbreakable under ordinary circumstances but is, in the end, exactly the same kind of bond a comet has with its own icy fragments. Given enough of an imbalance, applied quickly enough, that bond gives way exactly the same way. For the binary pair drifting toward the galaxy's center, that imbalance arrived all at once. As the pair swept in along its curving path, the star on the near side of the orbit began to feel the black hole's pull noticeably harder than its partner on the far side. At first the difference would have been small, the kind of gentle mismatch the pair might have shrugged off entirely on any ordinary approach to any ordinary star. But this was no ordinary star waiting at the center. With every passing moment, as the pair swept closer along its plunging path, that mismatch grew and grew and grew again, far faster than either star's own gravity could compensate for. Had there been any way to watch it happen up close, the two stars would have appeared to stretch, ever so slightly at first, their shared orbit no longer a neat, closed loop, but something being pulled long and thin, like a single drop of water drawn out between two fingers just before it splits in two. The two stars, still orbiting each other even as this happened, would have been swinging around their shared center faster and faster as the whole system tightened under the strain, the way a figure skater spins faster by pulling her arms in close to her body. Except here, nothing was pulling in. Everything was being pulled apart, faster and faster, right up until the moment it no longer could be. Somewhere in that final stretch, likely within a single close pass lasting no more than a matter of hours, the mismatch overwhelmed whatever modest pull the two stars still held on each other. The partnership, which might otherwise have lasted for billions of years, simply stopped existing. Not every such encounter would unfold in so orderly a fashion. The exact outcome depends on details as fine as precisely how close the pair's path carried it, and at what angle, and which of the two stars happened to end up nearer the black hole in that final approach. A slightly different geometry might destroy both stars outright, rather than sparing either of them. A slightly gentler pass might disturb the pair's orbit without fully breaking it apart at all, leaving two shaken but still bound stars to continue onward, changed but together. The clean, decisive split Hills described, one star captured and one flung free, was the most dramatic possible outcome, not the only one, which is part of why it would prove to be so rare, even among the already rare population of pairs that wandered anywhere near the black hole to begin with. What happened next unfolded according to the same principle that governs every gravitational interaction, dressed up in far more extreme clothing than usual. Energy cannot vanish. It can only move from one place to another. There is a much smaller, gentler version of this same basic idea in an old ice skating game some readers may remember from childhood, sometimes called Crack the Whip, where a long line of skaters joins hands, and the whole line begins to turn. The skater anchoring the line barely moves at all, while the skater way out at the far end goes flying, carried by speed borrowed from the whole line's collective motion, concentrated suddenly into just one person. Nobody pushes that last skater directly. The line's own turning motion does all the work. What happens near a black hole runs on the same basic principle, though comparing a game played on a frozen pond to what happens near an object with the mass of 4 million suns is, admittedly, comparing a garden hose to a waterfall. As the black hole's gravity worked on the pair, it did not destroy energy so much as redistribute it catastrophically, taking from one star and handing an enormous, lopsided share to the other. The star that ended up on the losing side of that exchange lost so much orbital energy so quickly that it had no way of continuing outward at all. It fell inward instead, captured, swept into a tight, fast orbit hugging closely around the black hole, joining whatever else already circled there. That captured star's new existence would look almost nothing like its old one, where it once traced a slow, stately orbit lasting thousands of years. It would now be swinging around the black hole on a path measured in years, sometimes less, whipping past at speeds that would have been unthinkable back in the quiet, ordinary neighborhood it came from. Astronomers who study the region today have found real stars living out exactly this kind of existence, whipping around Sagittarius A star on orbits so tight that some complete a full circuit in less time than it takes a person to grow from childhood into adulthood. A pace of orbit no star anywhere else in the galaxy could survive, keeping up for long, and yet somehow, remarkably, keep up with it they do, held in place by exactly the same unforgiving gravity that once shredded their old partnership apart. That star is not destroyed, not swallowed, not erased. It simply lives out the remainder of its life in the strangest, fastest, most crowded neighborhood the galaxy has to offer, forever within sight of the very thing that stole it from its partner. Its sky, if it could be said to have one, would look nothing like ours. No dark, restful nights, no familiar constellations wheeling slowly overhead the way they do out here. Only the crowded, blazing core of the galaxy in every direction, and somewhere close enough to dominate the view entirely, the warped light of background stars bending around the black hole itself. Over the full span of cosmic time, captured stars like this one become part of a slower, quieter story as well. Every star pulled in and held by the black hole in this way adds, eventually, a little more mass to it, one small addition among countless others accumulated across billions of years. The same encounter that flings one star toward the edge of the galaxy also, in its own patient way, feeds the very object responsible for flinging it. Destruction and growth, in this one particular corner of the galaxy, turn out to be the very same process, viewed from two different distances. The other star received the opposite gift. Instead of losing energy, it gained an enormous, sudden surplus, borrowed at its former partner's expense, and that surplus expressed itself the only way raw energy like that can, as speed. One moment, it had been half of an ordinary orbiting pair, indistinguishable from countless others scattered across the galaxy. The next, it was alone, and moving faster than almost anything else made of ordinary matter anywhere in the Milky Way. It would carry no visible scar from the encounter, no mark, nothing to set it apart from any other star of its kind, if you happened to glance at it through a telescope without already knowing its story. Its light would look the same. Its warmth, its color, its ordinary stellar life would continue exactly as before. Only its motion would give away what had happened to it, an entire violent history compressed into nothing more than a number. How fast, and in which direction? If either star happened to carry planets of its own, worlds orbiting closely enough to be swept along for the ride, those planets would share in whatever fate their star received. A planet circling the star that gets captured would find itself trapped in permanent orbit around a black hole, an existence almost impossible to picture clearly. A planet circling the star that gets ejected would be carried along at that same impossible speed, an entire small world, and anything that might ever have existed on it, taken completely and permanently out of the galaxy without ever having any say in the matter. Astronomers have never yet confirmed a planet surviving a journey like this one, but nothing in the physics rules it out, and the possibility alone is enough to make an already strange story stranger still. That first stretch of the journey would be the most crowded part of it by far. Before an ejected star ever reaches the comparatively empty, open spaces where our own sun spends its quiet existence, it first has to cross back out through the same dense, star-choked region it was born into, weaving, unguided, through a genuine crowd of countless other stars packed into a comparatively small volume of space. No star gets in its way on purpose. At the speeds involved, and across distances that dwarf every star's own physical size, a direct collision would be extraordinarily unlikely even in the most crowded part of the galaxy. But the region itself, glowing, turbulent, and busy, would have made for an extraordinary first few thousand years of a much longer journey, before the crowd finally began to thin, and the star found itself, for the first time, truly alone. There is no dramatic flash to mark that moment, no sound, nothing a distant observer could have seen happen in real time, even with the finest instrument pointed directly at it. Gravity does its work in silence. The whole sequence, from a peaceful, ordinary orbit to two entirely separate fates, likely unfolded in less time than it takes to read this sentence aloud, compressed into a single close pass near an object most of the pair's own galaxy will never come anywhere near. It is worth sitting, just for a moment, with how strange this actually is as a way for anything to happen. A star is not fired. Nothing ignites. Nothing detonates. Nothing pushes against it the way a rocket pushes against burning fuel. There is only gravity, curving the star's path so severely, so suddenly, that what began as an orbit simply never closes back on itself. The star does not know it has been launched. It only knows that the pull which once held it in place is, from one instant to the next, no longer strong enough to bring it back. This is part of what makes the whole process so difficult to ever catch happening in real time. A lone star, being shredded entirely by a black hole, announces itself, however briefly, with real light, a flare bright enough to be noticed from across the universe. A binary pair being quietly separated announces nothing at all. There is no signal to watch for, no alarm to respond to, nothing happening at the moment it happens that any telescope, however carefully aimed, could have detected. The only evidence left behind is the star itself, already gone, already racing outward, its entire origin story locked up in nothing more than its own trajectory, waiting for someone to notice it long after the fact. Clearing the black hole's immediate grip, as already established, is only the first obstacle in a much longer fight against the rest of the galaxy's combined pull. Not every ejected star wins that fight. A star tossed outward with only a modest surplus of speed behaves exactly like a ball thrown straight up into the air. It climbs, it slows, and it eventually falls back, no matter how hard the throw, so long as the throw fell short of what was needed. Only a star, carrying speed well beyond that threshold, keeps climbing forever, slowing gradually as the galaxy tugs at it from every direction, but never quite slowing enough to turn around. This is precisely why the mechanism Hills described stands apart from every other way a star can end up moving unusually fast through the galaxy, and it is worth being clear about the difference, because the sky is full of fast stars for reasons that have nothing to do with black holes at all. Some fast stars are runaways in a much more ordinary sense. When one member of a binary pair reaches the end of its life and explodes as a supernova, the sudden loss of mass can be enough on its own to unbind the pair completely. The surviving star, which had simply been orbiting at its usual modest speed right up until the moment of the explosion, suddenly finds nothing holding it in its old path any longer, and it continues onward in whatever direction it happened to be moving at that instant, like a ball released from a sling the moment the string is cut. The speed such a star carries away depends entirely on how fast it happened to be orbiting beforehand, and ordinary orbital speeds, even for close pairs, are nowhere near what a supermassive black hole can provide. The surviving star simply drifts off into the galaxy on its own, often still bright, often still visible for a long time afterward, but never approaching the extremes Hills was describing. Other fast stars are flung out through crowded stellar traffic jams, the dense, busy cores of ordinary star clusters, where 3 or more stars can pass close enough to each other for one to be gravitationally slingshotted away. This is a smaller, gentler cousin of what happens near a black hole, a genuine gravitational slingshot, but one involving nothing more than the modest gravity of ordinary stars, rather than the overwhelming gravity of a supermassive one. Globular clusters and other dense stellar nurseries scattered throughout the galaxy provide exactly this kind of crowded environment. Tens of thousands or more stars packed into a comparatively small ball of space, close enough together that near misses happen regularly on the scale of a stellar lifetime. A handful of stars crowded together can jostle and fling one another about, sometimes with real force, but nothing approaching what a single object with the mass of 4 million suns can deliver in one encounter. Both of those processes are real. Both happen regularly throughout the galaxy, and both, without exception, run into the same hard ceiling. An ordinary star's gravity, or the sudden violence of a supernova, simply does not have the raw energy budget to push anything beyond a few hundred kilometers a second, no matter how favorable the circumstances. That ceiling sits far below the threshold Hills calculated for a genuine encounter with the black hole at the galaxy's center. Only an object as extreme as Sagittarius A star, with its mass of roughly 4 million suns concentrated into so small a space, has enough raw gravitational energy on hand to push a star past that ceiling entirely, into the range of speeds that earn the name hypervelocity in the first place. A fast star is not necessarily a hypervelocity star. A hypervelocity star, by the very definition Hills gave the term, is something only a supermassive black hole can create. That distinction is not a technicality. It is the entire reason a hypervelocity star, if one could ever actually be confirmed, would be worth so much more than an interesting curiosity. A star simply moving fast could have come from any number of ordinary, well-understood processes happening all across the galaxy, all the time, all without any need for an invisible giant at the center. A star moving at genuine hypervelocity, on the other hand, points to exactly one plausible origin and one address. Its speed alone would be enough to rule out every gentler explanation, leaving only the single, extreme, and until now entirely unproven mechanism Hills had described. No gentler explanation would fit that kind of evidence nearly as well, and in science, an explanation that fits the evidence better than every rival is about the closest thing to certainty the field ever really offers. That is the strange gift hidden inside brute, indifferent physics. Run the numbers carefully enough, and even something this violent, this far away, becomes, in its own way, legible. All of this remained, for now, exactly what it had been from the beginning, a description of what should happen, built on nothing but careful reasoning and the unforgiving arithmetic of gravity. Every detail, the stretching, the sudden imbalance, the clean split into two opposite fates, the long climb outward against the pull of the whole galaxy, existed only on paper, worked out by one theorist with a pencil in an office thousands of miles from the nearest telescope capable of testing any of it. Every question the mathematics could answer, it had answered. How the pull grows as distance shrinks, how energy moves from one body to another, why one star would be captured and the other freed, why a genuine hypervelocity star could come from nowhere else. What remained were the questions no pencil, no notepad, and no amount of patient calculation could ever resolve on its own. Somewhere, out among the hundreds of billions of ordinary stars filling the galaxy, if Hills had gotten the physics right, some small number of stars were living out precisely the sequence just described, right now, invisibly, indifferent to whether anyone back on Earth had yet found a way to notice. Not one, not dramatically, not on any predictable schedule, but somewhere, sometime, across the galaxy's long history, the sequence had almost certainly played out before, and would play out again. The mechanism itself was no longer the mystery. What remained was the much harder question that had been waiting patiently since 1988, the question no amount of careful mathematics could ever answer on its own, whether anyone, ever, would actually catch one in the act. The star in question carried a catalogue name longer than most people would care to say out loud, so astronomers simply call it HVS1, short for Hypervelocity Star Number 1, the very first of its kind ever confirmed. Its velocity measured 853 kilometers a second, more than 1,900,000 miles an hour, the fastest speed ever recorded for a star in the galaxy's outer halo up to that point. Brown did not have to search for confirmation that something extraordinary had turned up. The number itself was the confirmation. Nothing in any of the ordinary well-understood processes astronomers already knew about, not a supernova's kick, not a crowded cluster's slingshot, could plausibly explain a single star moving that fast. News of the discovery spread quickly through the astronomical community, and for good reason. Confirming even one genuine hypervelocity star did more than validate a single theorist's decades-old idea. It offered indirect evidence of the black hole's mass and behavior that no other method could provide quite so cleanly, and it opened an entirely new way of studying the galaxy's history. Reading the trajectories of its most extreme escapees, like pages torn out of a much larger, otherwise unreadable book. For 17 years, Hills's idea had existed only as an answer, waiting for a question nobody had yet been able to ask out loud. Now, without any fanfare, without any dramatic search culminating in a triumphant announcement, the answer had simply turned up in the middle of somebody else's work, the way important discoveries in science often do. Jack Hills, by then no longer a young theorist but a scientist well into his career, lived to see his 1988 prediction confirmed. 17 years is not a terribly long wait by the patient standards of astronomy, but it is a long time to carry an idea nobody has yet been able to prove. And there is something quietly satisfying in knowing the physicist who first worked out the mathematics on paper was still there, decades later, when the universe finally handed back an answer. Picture the moment as plainly as it likely happened. Not a dramatic unveiling under a telescope dome at midnight, but an ordinary afternoon at a desk, a spreadsheet of measurements, one row among hundreds, looking distinctly, undeniably wrong. Most of the great turning points in recent astronomy have looked exactly like this from the inside, not a thunderclap, but a single number that refuses to make sense until you realize it is not a mistake at all. A number that big raises an obvious question, and it is not the question you might expect. The harder problem was never proving the star was moving fast. That much was already settled the moment the measurement came back. The harder problem was proving where it had come from, and there, the evidence available in 2005 was maddeningly indirect. A single measurement of speed tells you how fast something is moving away from you. It does not, on its own, tell you which direction that motion first began or where the journey started. Solving that problem took patience of an entirely different kind than the patience Hills had needed. Astronomers pointed the Hubble Space Telescope at newly discovered hypervelocity stars, not once, but twice, years apart, and compared the two images with extraordinary care. A star's true path across the sky, its proper motion, reveals itself only across a span of years, as the star's position shifts by an amount too small to see in any single snapshot, a difference sometimes no larger than a fraction of a single pixel in the image. Brown described the moment of finally measuring that shift as pretty exciting, and it is easy to understand why. Two photographs of the same patch of sky taken years apart would look, to any casual observer, completely identical. Only under the most careful, patient comparison does the tiny discrepancy reveal itself. A star's position shifted by a distance that would be invisible to the naked eye, even if you were looking directly at the page. The proper motion, once finally teased out of 2 patient years of separation between photographs, pointed directly back toward the center of the Milky Way, exactly where Hills had said, decades earlier, that the culprit ought to be found. It was not, however, an easy or a clean verdict every single time. Other researchers, examining their own hypervelocity candidates in these same years, proposed an entirely different birthplace for at least one of them, not the Milky Way's own center at all, but the large Magellanic Cloud, a smaller satellite galaxy orbiting our own. That particular star's chemistry and its position close to the neighboring galaxy, eventually settled the question in favor of the satellite galaxy rather than Sagittarius A star. A useful reminder that the label hypervelocity star describes a behavior, extreme, unbound speed, and not automatically a single confirmed address. Every candidate had to earn its origin story individually, through its own trajectory, its own chemistry, its own case, built patiently out of evidence, rather than assumed from the label alone. Over the years that followed, astronomers combed through many dozens of fast-moving stars in the galaxy's outer reaches, and the great majority of them, on close inspection, turned out to be something other than a genuine hypervelocity star from the galactic center. Some were simply measured incorrectly and turned out, on remeasurement, to be comfortably bound to the galaxy after all. Others belonged to the more ordinary population of runaway stars, cast off by an exploding companion or a crowded cluster rather than a black hole. At various points over the past 2 decades, researchers have compiled working lists running to several dozen candidates. The arrival of precision instruments like Gaia has since called a good number of those older candidates into question, trimming the confidently confirmed list back down considerably. The list of examples that genuinely hold up to the strictest scrutiny has always been small, and it has occasionally gotten smaller rather than larger, as better instruments quietly retired candidates that did not survive closer inspection. A single survey like Brown's can involve measuring the velocities of many thousands of individual stars, one at a time, patiently, most of them turning out to be exactly as ordinary as they first appear. It is unglamorous, repetitive work, the kind that rarely produces a headline right up until every so often it does. That lesson arrived with particular force in the case of a star catalogued as US 708, when it turned up, moving at hundreds of kilometers a second, faster than any ordinary star had any business moving. The excitement was immediate. Here, it seemed, was further proof of Hills's mechanism at work, another exile cast out from the galaxy's crowded, violent heart. The excitement did not survive close inspection. US 708 turned out to be something else entirely, a small, dense, stellar remnant called a helium white dwarf, the compact leftover core of a star that had already lived out its life. Its trajectory, once carefully reconstructed, pointed nowhere near the galactic center at all. The true story, pieced together over years of further study, involved a tight, doomed pair of white dwarfs locked in an impossibly close orbit, feeding material from one onto the other until the receiving star crossed a critical threshold and detonated in a runaway thermonuclear explosion, the same basic class of explosion astronomers use as a reliable cosmic measuring stick precisely because it always unfolds the same violent way. That explosion did not just destroy the star that produced it. It also severed, in an instant, whatever gravitational bond had held the pair together, hurling the surviving white dwarf away at extraordinary speed. No black hole required anywhere in the story. US 708 remains, to this day, one of the fastest stars ever measured in the galaxy, in some tallies faster even than the star that first bore the name hypervelocity. And yet, by the strict definition Hills had given the term back in 1988, it does not entirely belong in the same family as HVS-1 at all. It is a fast star with an entirely different biography, ejected by a stellar explosion rather than a black hole's tidal grip, a reminder that raw speed, however extraordinary, is a clue to be investigated rather than a verdict to be assumed. The two stories look similar from a distance. Read closely, they describe two completely different kinds of ending. That distinction matters for reasons well beyond bookkeeping. Every time a fast-moving star turns up, The same question has to be asked all over again, patiently, without assuming the answer in advance. Fast because of a black hole, or fast for some entirely different reason? Getting that question wrong, even once, would mean crediting Sagittarius A star with an escape it never actually caused. The bookkeeping is tedious. It is also, in its own quiet way, exactly how science protects itself from telling a better story than the evidence actually supports. The years following HVS-1's discovery turned a lucky accident into a genuine, deliberate hunt. Brown and his colleagues built a targeted survey specifically to find more stars like it, searching systematically rather than waiting for another lucky afterthought. The instrument of choice for measuring a star's speed is the spectrograph, a device that spreads a star's light out into its full rainbow of colors and reads, in the precise position of certain dark lines within that rainbow, exactly how fast the star is moving toward or away from us. The same basic stretching and compressing of light already described earlier in this account, applied now with the patient precision needed to measure a difference of a few kilometers a second across tens of thousands of light years of empty space on stars too faint to ever notice with the naked eye, tucked among thousands of others in a single night's worth of data. That technique, patient and painstaking, added a small but growing number of new hypervelocity candidates to the list over the following years. Most of them, like HVS-1, hot, bright, blue-white stars. The same kind of star this whole story predicted would be born in the crowded, gas-rich neighborhood surrounding the black hole. That pattern held for well over a decade, long enough that it began to look like a genuine rule rather than a coincidence. Every confirmed hypervelocity star, without exception, turned out to be young, massive, and blue. It made a certain kind of sense. Massive, hot stars burn brilliantly and live fast, which makes them far easier to spot at enormous distances than a smaller, dimmer star would ever be. But a rule built entirely out of what happens to be easiest to see is not necessarily a rule about what is actually happening across the whole galaxy. It could just as easily be a rule about the limits of 1980s and early 2000s era telescopes, mistaken for a rule about physics. The next major leap forward, arriving 14 years later, had less to do with cleverness than with sheer scale. A European Space Agency spacecraft named Gaia spent the past decade mapping the positions and motions of more than 1 billion stars, cataloging our galaxy with a precision earlier generations of astronomers could only have dreamed about. Where Brown's original search had turned up its discovery through one afterthought measurement, Gaia offered something closer to a census, an entire galaxy's worth of stars, measured all at once, waiting for anyone patient enough to comb through it for exactly the right kind of anomaly. Working from that flood of new data, in 2019, a survey combining this precise sky mapping with ground-based measurements of stellar speed identified a star now known simply as S5HVS1, a designation that also happens to record the very survey that found it. This star did not merely join the list, it rewrote the top of it entirely. The whole shape of this hunt has changed almost beyond recognition since 2005. Where Brown's original discovery came from one astronomer's careful attention to a single anomalous number buried inside a survey built for another purpose entirely, today's discoveries increasingly come from enormous, automated instruments built to answer entirely different scientific questions, sifting through data so vast that no single person could ever examine it star by star. Gaia was built to map the positions and motions of an entire galaxy, not hunt fugitives fleeing its center. And yet, again and again, these vast instruments aimed at questions that have nothing to do with any single runaway star, keep stumbling across exactly the kind of star Hills first imagined, almost as a footnote to their real work. The ground-based half of that survey carries its own formal name, the Southern Stellar Stream Spectroscopic Survey, shortened by the astronomers who use it daily to simply S5, the same S5 that now forms half of this star's official designation, confirming this star's origin did not require years of patient waiting between snapshots, the way it had for the very first discovery back in 2005. Gaia's own extraordinarily precise measurements of position and motion, combined with the ground survey's measurements of speed, let astronomers reconstruct the star's full path through space almost immediately. Not just how fast it was moving, but the exact direction it had come from, extended backward across tens of thousands of light years until it converged, with remarkable precision, on the galaxy's very center. What had taken the original 2005 discovery years of patient follow-up to establish, this newer dataset could largely settle within a single, comprehensive pass. This new record holder is currently moving at roughly 1,755 kilometers a second, well over 3,900,000 miles an hour, faster than any other star ever confidently tied back to the galaxy's center. It is an ordinary main sequence star by type, a little more than twice the mass of our own Sun, the kind of star that, born anywhere else in the galaxy, would have lived out an unremarkable existence. Calculations based on its speed and its current position, roughly 29,000 light-years from Earth, suggest it was ejected from the immediate neighborhood of Sagittarius A star at a speed close to 1,800 kilometers a second, and that it has been traveling outward, alone, for about 4,800,000 years, a journey that began long before the first members of our own species walked anywhere on Earth. Unlike some of the earlier candidates, whose birthplace required careful argument and years of patient follow-up observation, this star's path points back toward the galactic center with a clarity that leaves very little room for doubt. Of every hypervelocity star, confirmed since Hills first put pencil to paper, this is the one astronomers point to as the cleanest, most unambiguous example of his prediction playing out exactly as described. For years afterward, that pattern about young, massive, blue stars held firm, right up until a discovery reported only weeks before this very account was written. A team led by astronomer Shenhong Deng, working with an instrument called the Dark Energy Spectroscopic Instrument, built to map the accelerating expansion of the universe rather than hunt for individual runaway stars, turned up something that did not fit the mold at all. A hypervelocity star candidate estimated to be roughly 14 billion years old, nearly as old as the universe itself, small, cool, and only about 80% as massive as our own Sun. Moving at roughly 523 kilometers a second, this ancient wanderer is fainter and far less dramatic to look at than S5HV-S1. It may also be far more important. Astronomers describe its status carefully as a strong candidate rather than a fully closed case, the newest addition to this account, and still, at the time of this telling, working its way through the same careful scrutiny. Every claim like this one must survive before it earns a permanent place on the confirmed list. Its faintness is only part of what makes it so unusual. Stars are built, generation after generation, out of material enriched by the deaths of the stars that came before them, each new generation carrying a slightly heavier mix of elements than the last. A star this old carries almost none of that later enrichment, chemically closer to the raw hydrogen and helium left over from the earliest days of the universe than to a star like our own Sun, born billions of years later. out of gas, already seasoned by countless earlier stellar lifetimes and deaths. Finding a star with this particular chemical fingerprint moving at hypervelocity speed does not just add one more name to a short list. It pushes the whole story back to nearly the beginning of everything. Hills's original 1988 prediction never actually specified that only young massive stars could be ejected this way. The mathematics worked for any binary pair unlucky enough to wander close enough to the black hole, regardless of the star's age or size. The apparent pattern toward young, massive blue discoveries was always, as some researchers suspected for years, more likely a reflection of which stars happened to be easiest to spot than a genuine rule of the underlying physics. If confirmed, this find suggests that everything astronomers thought they understood about hypervelocity stars for the past 2 decades was shaped as much by the limits of their instruments as by the actual physics playing out at the galactic center. Small, old, faint stars are simply much harder to notice against the crowded backdrop of the galaxy than young, hot, blue ones, whether or not they are moving at extraordinary speed. If Hills's mechanism has been quietly ejecting stars of every size and every age across the galaxy's entire history, and not only the young and the massive, then the population of hypervelocity stars scattered through the galaxy's halo may be far larger, far older, and far more varied than anyone had previously guessed. This particular candidate's ancient age, in particular, carries its own quiet significance. If it truly came from the galactic center, it means the mechanism Hills described was already at work when the galaxy itself was young, flinging stars outward for nearly the whole of cosmic history, long before human beings existed to wonder about any of it. There is something almost dizzying in the timing of it. A star that began its outward journey when the universe itself was still finding its shape long before the sun or the earth existed in any form was only confirmed, only finally noticed and measured and understood for what it was. Within the same handful of weeks, this very account was being written. 14 billion years of solitary travel, and human beings only just caught up to it. More such stars, astronomers now suspect, are almost certainly waiting to be found, hidden in plain sight among the galaxy's ordinary, unremarkable, decidedly unglamorous stellar population, indistinguishable from their neighbors, except for the one number that, once finally measured, gives everything away. Consider the span these few confirmed examples cover. One star's outward journey began less than 5 million years ago, a heartbeat in the life of a galaxy that has existed for more than 10 billion years. Another, if this newest and strangest candidate holds up to further scrutiny, began its own journey when the universe itself was still assembling its first generation of galaxies. Between those two extremes sits nearly the entire history of the Milky Way, and scattered somewhere across that whole vast stretch of time, quietly, invisibly, this exact sequence has been repeating. Taken together, these discoveries turn Hills's 1988 prediction from an elegant, unproven idea into a confirmed, ongoing feature of how our galaxy behaves. A star can be born deep in the crowded heart of the Milky Way, live out an entirely ordinary existence alongside a companion for who knows how many millions of years, and then, in the span of a single close pass near an object it could never have seen coming, be cast permanently out of the only galaxy it will ever call home. It has happened to a star discovered by accident in 2005, to at least one star whose supposed membership in this exclusive club turned out, on closer inspection, to belong to an entirely different and unrelated story, to a star found through Precision Sky mapping in 2019, still climbing toward the edge of everything. And if this newest and strangest case holds up to at least one wanderer, old enough to have been watching the galaxy take its current shape, by any honest, careful reading of the evidence gathered so far, the mechanism is proven. The examples, however few and however hard-won, are real, named, measured stars, not hypothetical ones, their velocities recorded to the kilometer, their positions tracked across years of patient observation, their origins traced backward across tens of thousands of light years, until the evidence leaves no honest room for doubt. What remains is not a question of whether any of this happens. It is a question of what comes next, what becomes of a star, and everything that might once have belonged to it, after the moment its light is written into every telescope database as belonging to something already, irreversibly, on its way out. Every one of these confirmed stars, it is worth remembering, represents only half of an original story. Somewhere behind each of them, presumably, sits a former partner, captured rather than freed, still circling close to Sagittarius A star within the crowded, chaotic swarm of stars already crammed into that neighborhood. Astronomers have not managed to identify any specific captured partner belonging to any specific escapee, a task considerably harder than finding the escapee itself. For now, each of these confirmed stars can only tell its own half of what was once, briefly, a shared story, the other half orbiting on, unreachable, somewhere in the crowded dark none of our instruments can yet fully see into. 29,000 light years from here, one particular star is still climbing, still slowing under the patient, insistent pull of everything it left behind, with a great deal of its journey yet to come. Where it is actually headed, and what it will find, or fail to find, when it finally gets there, is a very different question than the one this account has been answering so far. Where it is headed depends on a question astronomers have never fully settled. Where exactly does the Milky Way actually end? It sounds like it should have a simple answer. It does not. The bright, familiar disk of stars, the part most people picture when they hear the word galaxy, stretches roughly 100,000 light years across, a figure precise enough to print in a textbook. But stars continue well past that comfortable boundary, scattered thinly through a much larger, dimmer halo that some studies now trace out to nearly 2 million light years across, folding in an enormous, largely invisible reservoir of dark matter along the way. Ask 3 different astronomers where the galaxy truly ends, using 3 different honest definitions, and there is a real chance you will get 3 different answers, each one defensible, none of them final. None of this uncertainty comes from carelessness. The astronomers measuring these numbers are some of the most careful people working in any science today. It comes instead from the nature of the thing itself, an object so vast and so diffuse at its edges that even the best instruments available struggle to say with confidence exactly where it stops being a meaningful boundary and starts being simply more of the same thin scattering of matter that fills most of the universe. The galaxy, it turns out, does not have an edge so much as it has an ever-thinning fade, less like the wall of a house and more like the last, faint light of dusk, with no single instant you can point to and call the exact moment day became night. Some researchers draw the boundary where the density of stars finally drops to nearly nothing, putting the edge at a few 100,000 light years out. Others insist the true boundary has to include the dark matter halo as well, since that invisible material is still, gravitationally, very much part of the galaxy, which pushes the honest edge dramatically farther, by some recent estimates, out toward a diameter approaching 2 million light-years. Both answers are defensible. Neither one is wrong, exactly. They are simply measuring different things and calling them by the same name. That uncertainty is not a failure of measurement. It is an honest reflection of what the outer galaxy actually is. Not a boundary, but a gradient, growing sparser and sparser the farther out you look, until at some point, impossible to pin to an exact distance, there is simply too little of the Milky Way left to call it the Milky Way anymore. For the star this account has been following since it was flung from the immediate neighborhood of the black hole, that uncertainty is not an abstract debate. It is the actual shape of the road still ahead of it. None of this is guesswork in the casual sense. Astronomers calculate a star's future path the same patient way they reconstruct its past one, by carefully modeling the combined gravity of everything in and around the galaxy, then running the star's current position and velocity forward through that model, checking the results against every other star whose motion has already been measured and confirmed. The further out such a projection reaches, the less certain any single detail becomes, but the broad shape of the outcome, an eventual, permanent departure, is about as settled a conclusion as this particular science currently offers. Even using a comparatively modest estimate for where the galaxy's gravitational influence finally fades to nothing, a star moving at its current speed would need tens of millions of years more before it could be said to have genuinely, unambiguously left. Measured against the 4,800,000 years it has already spent traveling, that is not a small remaining distance. It is the greater share of the journey, still ahead, still unfinished. There will be no ceremony to mark the actual moment, whenever it comes, whichever honest definition of the boundary eventually applies. No instrument will chime, no astronomer will look up from a screen and announce that it has happened. The star will simply continue along the path it has followed since the moment of its ejection, and at some unmarked point along that path, indistinguishable in the moment from the point just before it, the Milky Way will have released its last meaningful claim on it. It will have already happened, in the past tense, well before anyone could ever say it was happening. Tens of millions of years is not a span of time human experience offers any honest comparison for. It is not simply longer than a lifetime the way a redwood tree's lifetime is longer than a human one, a comparison that at least still shares the same basic unit of measurement. It is longer than the existence of our own species by a factor large enough that the comparison stops being useful past the first few zeros. Whole mountain ranges will rise and erode to nothing in the time this one star spends simply finishing its exit. Species will emerge, flourish, and vanish entirely, replaced by others that will do the same, many times over, before this particular journey is finished. None of that will register, even slightly, to the star itself. It has no calendar. It has no stake in what happens on any world it might once have warmed. It simply continues outward, at the same steady, indifferent pace, regardless of what unfolds, or fails to unfold, anywhere within reach of its fading light. The view from that star, if there were anyone aboard a planet to see it, would change gradually rather than all at once, the way a familiar road slowly empties out the farther you drive from a city, house by house, streetlight by streetlight, until eventually there is only dark road and open country left. For the first stretch of the journey, the crowded galaxy the star was born into would still dominate the sky entirely, a dense, glowing band of countless neighbors. Further out, that band would thin. Individual stars, once packed so closely together they blurred into a single haze of light, would separate into countable points, then scattered points, then finally, after a long enough journey, isolated points, so far apart that most of the sky between them would be genuinely, properly empty for the first time. The stars themselves would not vanish so much as spread thinner. The familiar patterns people have named and renamed across thousands of years of human history gradually losing their shape entirely. Individual points drifting from this new and constantly shifting vantage point into arrangements no constellation chart back home had ever anticipated. Even the quality of the darkness itself would change along the way. Out here, near our own sun, the black between the stars is never entirely empty. It carries faint traces of scattered starlight, of glowing gas, of the accumulated glow of a crowded galaxy, pressing gently on every direction you look. Farther out, that glow would fade a little more with every passing million years, the darkness growing steadily more complete, more absolute, until it approached something closer to the true, unfiltered blackness of space itself, largely unsoftened by anything nearby enough to fill it in. Anyone born into that later darkness, if anyone ever could be, would have no memory of it being any other way, no sense of loss attached to a crowded sky they never actually knew. Absence only feels like absence to something that remembers the alternative. To a hypothetical observer who had only ever known the emptying sky would simply be the sky, unremarkable, exactly the way tonight's crowded one feels unremarkable to us. Eventually, and this would take longer still, even the Milky Way's overall shape, the great, glowing disk that anchors this entire account, would begin to shrink into something closer to a single, distant smudge of light, still the brightest thing in that sky, but no longer a place, no longer home in any meaningful sense. Simply the direction the star had once come from, a landmark receding the way a coastline recedes behind a ship that has no plan and no ability to ever turn back. This is not a story about death. Unlike so many of the galaxy's more dramatic tales, nothing here explodes, nothing collapses, nothing runs out of fuel and quietly fades away, the far more familiar ending most stars eventually share. This is a story about departure instead, a different and in some ways stranger kind of ending, one where the star involved keeps on doing everything a star does, perfectly healthy, perfectly intact, simply somewhere else, and getting a little further away with every year that passes. None of this happens to the star itself in any way that threatens it. It is worth saying plainly, because the temptation to treat this as a tragedy is strong, and it would not be an honest one. The star does not suffer for any of this. It does not run short of anything it needs. It continues doing exactly what stars do, fusing hydrogen into helium at its core, radiating light and warmth outward in every direction, entirely unbothered by the question of who, if anyone, is close enough to receive any of it. A star that finds itself utterly alone burns exactly as steadily as a star crowded among billions of neighbors. Gravity may have written this particular star's exile. It had nothing to say about the star's health, or its warmth, or how long it has left to live. There will come a point, well beyond the tens of millions of years already discussed, when even our most capable instruments will simply lose track of the star, its light stretched thin across a distance too great, and a brightness too faint for any telescope to meaningfully follow. Science does not get to watch every story through to its actual end. At some point, quietly, the data simply runs out, and the star continues on regardless, entirely unconcerned with whether anyone is still counting. How long that is depends on the star itself. A star like the one this account has followed most closely, a little more than twice the mass of our own sun, burns through its nuclear fuel considerably faster than a modest star like our own does. Where our sun is expected to shine steadily for something on the order of 10 billion years altogether, A star of this larger size will likely live for somewhere closer to 1 billion, still an immense stretch of time, one that comfortably dwarfs the tens of millions of years remaining in its outward journey. This particular star, in other words, is very likely to complete its exile from the galaxy with time to spare, living out whatever remains of its natural life in the genuine emptiness beyond, rather than ending along the way. Our own sun, for whatever comfort it offers, will never share this particular fate. It sits too far from the galactic center, orbits too safely, moving at a comfortable, unremarkable pace through a comparatively quiet stretch of one of the galaxy's outer spiral arms, and will spend the whole of its existence gently circling the Milky Way exactly the way it always has, never wandering anywhere near Sagittarius A star, never facing anything like the fork in the road this account's star encountered. It will simply age in place, swelling eventually into a red giant several billion years from now, before settling into a slow, quiet retirement as a white dwarf, still orbiting the same galactic center it always has, never once leaving home. What waits for it after that, in the genuine emptiness beyond any galaxy's edge, is mostly more of the same emptiness. The space between galaxies is not entirely without structure. Faint bridges of gas connect some neighboring galaxies to one another, and the occasional wandering star, ejected the same way this one was, or by some other violent process entirely, drifts through that space, alongside it, far enough apart that the two would likely never cross paths or even notice each other's light. Mostly, though, intergalactic space is simply what its name suggests. The space between, vast beyond ordinary description, home to a whisper of gas and dust so thin it barely deserves the word matter at all. Astronomers have a name for exactly this population: intracluster stars, orphaned suns that no longer belong to any single galaxy, drifting instead through the space between them, bound only to the combined gravity of an entire cluster of galaxies rather than to any one galactic home. They have been found before, in other galaxy clusters, glowing faintly enough that they show up not as individual points of light, but as a dim, diffuse haze filling the space between galaxies, the accumulated glow of countless stars too scattered and too faint to pick out one by one. This particular star, once its own journey is finally complete, will join exactly that population. One more, anonymous point of light, contributing its own small share to a glow no single telescope will ever resolve back down to its individual source. The wider structure surrounding all of this, the arrangement of galaxies themselves across the universe, follows its own grand pattern. Threads of galaxies strung together like beads along a vast, three-dimensional web with enormous, comparatively empty voids filling the space between the threads. Our own galaxy sits along one such thread, part of a small, gravitationally bound cluster that includes Andromeda, our nearest large neighbor, along with dozens of smaller companion galaxies. An intergalactic star, in other words, does not necessarily mean a star adrift in true, universal emptiness. More often, it means a star that has simply changed its address within that same wider structure, trading one galaxy's gravity for the broader, gentler pull of the whole cluster surrounding it. A star finding itself there would not be unique in any absolute sense. Other stars, ejected from other galaxies by other black holes, or flung loose during ancient galactic collisions, almost certainly already drift through that same intergalactic dark, unseen and unaccounted for, each one carrying its own version of exactly the story this account has told. But relative to any single galaxy, relative to any world that might have circled it, or any night sky that might once have looked up at it as one star among billions, that star would be as alone as a single object can meaningfully be. Everything this account began with, the comforting, familiar, endlessly repeating night sky, the same stars your grandparents saw, the same patterns wheeling overhead night after night, belongs entirely to the crowded side of that divide. It is worth returning to that image now, because the star's departure changes it more than it might first appear to. The night sky feels permanent because nothing about looking up at it on any single ordinary night gives away what is actually happening. Nothing in the experience of stargazing announces that the sky is, in its own unhurried way, in motion, shedding pieces of itself the way a tree sheds leaves. It will never grow back. You cannot see it happening. You are not meant to. The timescales involved are too vast, the individual events too rare and too quiet for any single human lifetime to register more than the faintest, most theoretical hint that anything is different tonight than it was on any other night, stretching back through everyone who has ever looked up before you. But it is different. Somewhere in the galaxy tonight, whether or not any telescope happens to be pointed the right way at the right moment, the sequence this account has described in such patient detail is very likely unfolding again, exactly as it has, by the evidence gathered so far, unfolded across nearly the whole of the galaxy's existence. A pair of stars, bound together for longer than either could ever have understood, wanders too close to the quiet giant at the center. One is kept, one is cast out, and the galaxy, the whole vast, star-filled structure that feels from underneath it as steady and as finished as anything in this world, continues on exactly as it was a moment before, one star lighter, indifferent to the loss, in a way that would be almost unsettling if it were not so plainly, mathematically ordinary. The same force that built this galaxy, that gathered a thin, formless cloud of primordial gas into hundreds of billions of individual, burning suns arranged into elegant, sweeping arms, holding the whole structure stable for more than 10 billion years, is the exact same force responsible for this one star's exile. Gravity does not choose between building and unbuilding. It simply is what it is, indifferent to whether its work on a given night gathers a galaxy together or sends one small piece of it flying permanently apart. The architecture and the exile come from the identical set of rules, applied at different distances, under different conditions, with no more intention behind one outcome than the other. That is the truth this account has been slowly building toward, and it is a smaller, quieter truth than it might first sound. The Milky Way is not a finished thing. It is not a monument, fixed in place, handed down complete and unchanging the way it can feel on a clear night from a porch or a field or the back seat of a car with the windows down. For whatever remains of its existence, this star will not have a home in the sense every other star visible in tonight's sky still does. It will not belong to a galaxy the way our own sun belongs to the Milky Way, wrapped in the gravity of hundreds of billions of companions, sharing one single sweeping orbit with all of them. It will simply be present in space, still burning, still real, still exactly as much a star as it ever was, but unanchored in a way almost nothing else visible from Earth tonight actually is. The Milky Way, meanwhile, carries on. It is closer to a process still running, a structure that has never once stopped rearranging itself, gathering some stars inward while letting others go, on timescales so much longer than a single human life, that the difference between motion and stillness simply stops being something we are equipped to notice directly. Every telescope image of the Milky Way you have ever seen, every star chart, every planetarium ceiling, is a single frozen frame pulled from something that has never actually stood still, presented to us as though it were a photograph of something finished, because a single human life is simply too brief a shutter speed to catch it in the act of changing. The sky above you tonight is not the same sky your grandparents saw. Not exactly, not down to the last star. It only looks that way from here. There is no lesson to draw from this, beyond the plain fact of it. The stars are not sending a message. The galaxy is not trying to teach anyone anything about impermanence, or about holding on loosely, or about any of the tidy morals a story like this one might seem to invite. It is simply, mechanically true. Even something built from hundreds of billions of stars, held together by gravity strong enough to bend the path of light itself, still loses pieces of itself, quietly, continuously, and always will, for as long as there is a black hole at its center, and binary stars unlucky enough to wander near it. Permanence. At every scale this account has touched, from a single partnership between two ordinary stars to the shape of the galaxy that holds them, turns out to be a matter of degree rather than a fact. Some things simply last long enough to feel unconditional. None of them actually are. Nothing about any of this makes the Milky Way special either. Nearly every large galaxy astronomers have ever studied carries its own supermassive black hole quietly anchoring its center, and very likely enacts some version of this same slow, patient exile on its own binary stars. Galaxy after galaxy, scattered across the observable universe, each one running an identical, indifferent process, each one shedding its own small, steady trickle of stars into the emptiness between galaxies, largely unnoticed, for exactly the same reason this one does. Multiply this single quiet event by every large galaxy visible to our best telescopes, by the hundreds of billions of galaxies scattered across the observable universe, and the scale of what is actually happening at any given moment across the universe as a whole becomes almost impossible to hold in mind all at once. Somewhere, right now, countless versions of the exact sequence this account has described are almost certainly unfolding, unnoticed, unrecorded, in galaxies too distant for any instrument we currently possess to ever resolve down to the level of a single star. The other stars this account has followed are, each in their own way, somewhere along this same unfinished road. The very first confirmed example, found by accident in 2005, has been climbing outward even longer, its own exact position and remaining distance still being refined by ongoing observation. The ancient, faint wanderer, identified only weeks before this account was written, carries an age that raises an honest, still unanswered question. Exactly how far such a star can travel in 14 billion years is not yet fully worked out, and its precise current position, unlike the record holder this account has followed most closely, has not yet been pinned down with the same confidence. What can be said plainly is that if its age holds up, it has had more time to travel than almost any other confirmed example by an enormous margin. None of them will ever cross paths with one another again. Each is simply, separately, quietly finishing what a single close encounter with a black hole started. Astronomers cannot say precisely when the next confirmed example will turn up, only that, given how many of the ones already found were stumbled upon by pure accident, buried inside surveys built for entirely different purposes, another discovery seems less a question of if than of when. Somewhere in an archive of data already collected, perhaps sitting quietly on a hard drive at this very moment, the next one may already be waiting patiently for the right person to notice one number that simply does not belong. The census of confirmed examples will almost certainly keep growing in the years ahead. Newer surveys, more sensitive instruments, longer stretches of patient observation, all promise to turn up additional stars living out this same sequence, each one adding another data point to a picture that, even now, remains genuinely incomplete. It is entirely possible that within the next decade, the handful of confirmed cases this account has described will look, in hindsight, like the earliest, roughest sketch of a much larger and better understood population. Astronomers have not stopped watching any of them. Each remains, to this day, an object of continued study, its position and speed measured and remeasured as instruments improve, its predicted trajectory refined a little further with every new observation. There is no reason to expect any dramatic new chapter in any of these particular stories. Each star will simply keep climbing exactly as predicted for as long as anyone continues watching, and very likely for a great deal longer than that. There is a particular quality to an ending like this one, quieter than grief, because nothing about it involves anyone doing anything wrong or anything being taken that should have been kept. It is closer to the quiet of an empty chair at a table that used to seat two, not tragic, not even especially sad, just a small, permanent adjustment to how the room is arranged from now on. The star that began this particular account is still out there tonight, further along than it was when this account started, closer to a threshold no one has ever precisely marked, carrying a story that will not finish for tens of millions of years still to come, indifferent to whether anyone back on the small, quiet world it left behind ever thinks of it again. It does not know it is alone. It does not know it was ever anything else. It simply continues, the way every star continues, doing exactly what stars do, in a place that, however empty, is now, and will remain for a very long time, entirely its own. Sleep now. Somewhere, one small star is still, quietly, drifting farther from home,